Log on, tune in, find out. Another good idea from Cambridge.
Alina Chertock here, she's a regular visitor to the temp, but maybe the first time at the Newton Institute. Alina is from North Carolina State University, and she's going to speak to us today on interaction dynamics of singular wavefronts computed by particle methods. Please.
Thank you very much. Thank you very much for the invitation. It's indeed my first time in the institution, and I thank you for giving me an opportunity to speak here. And I will talk about interaction dynamics of singular wavefronts computed by particle method. And this is a joint work with Philippe Dutoit and
Alina, maybe you can turn on the microphone.
I did. Okay. So can you hear me?
No, it doesn't sound like a microphone.
Put it up. Put it up.
Put it back.
Yeah, a bit more up.
Hello. Hi.
It's okay.
Can you hear? Oh, okay. And so this is the joint work with the Philippe Dutoit and Gerald Marsden, who unfortunately passed away at about 2 weeks ago, lost his battle with the cancer. So I will dedicate this talk to his memory, and I will be talking about, first of all, the application of the equations, and we're interested in the internal waves. So those are different from the surface shallow water waves, and these internal waves, they oscillate within the ocean or atmosphere, and they arise from the perturbation to hydrostatic equilibrium. And a simple example which can be given on such waves, it's the wave propagation on the interface between two different fluids of different densities. And when this equilibrium is perturbed, these waves start to appear, and they typically have very low frequencies and higher amplitude, and they propagate for long distances deep down the ocean. So what we are interested in the modeling these internal waves, and here I have some pictures, which it's very difficult to have any picture of these waves because they propagate, as I mentioned, very deep in the ocean or atmosphere. So here you have an artificially colored image from the space of the Strait of Gibraltar, shows these internal waves over here and their propagation, and another picture from the radar where you have these internal wave propagating, and they reconnect, so they interact, and they appear after they exchange momentum during this nonlinear interaction and then reappear again, and we will discuss these properties of the waves. And yeah,
How deep down are these waves in the sea? Or?
I think it's 100. I think it was just they propagate about. So they may be like 100 meters tall, so they propagate very deep in the ocean. I'm not sure how deep, but I'm not sure right now. So what we are interested in, we are looking at this equation, which is called Euler-Poincaré equation associated with the diffeomorphism. Shortcut EPDIF equation, and it's a model of this active fluid transport. And here you have an equation, two equations, a system actually. U is the fluid velocity and m is the wave momentum, and they so this is a hyperbolic equation, but here what you have a global relation between u and m, which are connected through the modified Helmholtz operator equation, and this system of equation models the internal waves as a delta function. So you think about the momentum as being a delta function distributed along the curves in the plane or surface, and it actually corresponds to modeling these internal waves as contact discontinuities. And And again, as I said, this relation between the velocity and momentum is non-local, which makes the development of numerical method quite challenging. And here I give some references. So as I said, these solutions of this EPDF equation is a contact discontinuity that carry momentum, and when the front interacts, they undergo through a collision, and in which the momentum exchange, and then they reappear again, is actually in the same form. And this behavior is actually very similar to behavior of solitons of the KdV equation. So here are some references. This equation is actually coincides with the Kamasa-Holm equation for the shallow water in 1 and 2D. Interesting enough that people working on average template matching and also in computational anatomy, they use this equation to describe the singular solution, to describe some geometrical structures and the landmarks. And as I will show you in a moment in a very simple example, then applying proper viscosity and also enforcing incompressibility can produce a Navier-Stokes alpha model of turbulence. So just a brief slide where I show the one-dimensional EPDF equation. And here it's just a Kamasa-Holm equation for shallow water. And here I show you that it's a dispersionless limit of Kamasa-Holm equation. So if you take this original Kamasa-Holm equation and the right-hand side make it 0, so you recover the Kamasa-Holm equation, while if this alpha is 0, then you will recover the celebrated Kordovec-de Vries equation. Also, you can add the viscosity to the equation, and then if alpha goes to 0, what you will recover is just the Burger's equation. What is interesting about this equation, so essentially in 1D everything is known, and this is the equation which is integrable. So it has infinitely many conservation laws. It's bi-Hamiltonian, and from having these two Hamiltonians you can build infinitely many Hamiltonians and pairs, and you can show that the system is completely integrable. It's non-local, and it has a very interesting unusual solution properties. So these solutions are actually non-smooth. There's contact discontinuities which they have a discontinuity in the peak of the wave is actually in the first derivative of the solution, and even if you start with the smooth initial data. And this is what I just said about system being Hamiltonian, actually bi-Hamiltonian. You can start by showing that these two Hamiltonians are conserved within the system, and then you can take a Hamiltonian pair which will be still a Hamiltonian, and from here you can build an infinitely many number of conservation laws actually show that the equation is completely integrable. Just to give you an idea, an intuition of what the solution of this equation may look like, let me just do a very simple exercise real quickly. I'm taking this M, substituting into this one-dimensional equation. I'm getting the equation in terms of U only, and then I seek a solution in the form of the traveling wave. Again, it's a very simple exercise. If you look for the solution as a traveling wave, substitute this capital U in this second line, you obtain the ODE, which you can solve easily. And after solving this ODE, you see that the solution look like a constant times to the exponent to the power negative absolute value x minus the same constant ct over alpha, and c is actually equal to u maximum. So what you can see that the solution is the form of the traveling wave, which has a discontinuity in its first derivative due to the absolute value, and it propagates preserving its shape either to the left or to the right, depending on the sign of c, and the speed of propagation is proportional to the amplitude of this wave. And one can make an n-picon solution ansatz and say that, for example, so and this solution is called picon, and one can make a solution ansatz saying that if this one of these exponent is the solution, then since the system is completely integrable, it turns out that you can take a linear combination of this picked solution, and it still will be a solution of the system. And it's moreover these coefficients p and q corresponds to the location of the peak, and p is actually its amplitude. They satisfy the canonical Hamiltonian equation, whereas Hamiltonian is given by this formula. So also, just for simplicity, again, just here I'm giving you an idea how the solution behaves. You can consider initially two picons, two waves, located at two different points, Q1 and Q2, having amplitude P1 and P2, and they initially are separated by the distance gamma. If you take two of them, you can easily solve the system, and if you denote by P capital P1 plus P2, so you make a change of variables, which is written here, you get a system of ODE for P capital P small Q capital Q. You solve it, and again the solution is written here. What you can actually see that the total momentum of the system, the total mass is conserved. But what is interesting is that if you start with two picons which are of the opposite sign, they actually can overlap, and they can. So what can happen? It's shown here on the picture that you can start with two picons. One is positive, one is negative. The positive one will move to the right, and the negative one will move to the left. At some point, they will overlap, and the solution will become zero. And interestingly enough, so if you think about zero being a solution, especially if you try to solve the problem numerically, once you get zero, you get zero. But physically, which is the weak solution, which is the obviously correct solution to the problem, but there is another solution which obtained after reconnection of this. So they actually reappear from zero again in exactly the same shape with the shift phase shift. So it's a very interesting phenomena, and it actually gives a lot of challenging tasks for numerics, and there are a couple of them. First of all, I already mentioned that when you have these overlap solutions, again, numerical method, if you use finite difference or finite volume method, any finite different type method, again, once the two peaks overlap and you get zero, you cannot get out of there with finite difference, whatever method. So, but you would like to derive a method which will recover soliton behavior of these two peaks. And also a very difficult and very challenging task is actually to get a very good resolution where the contact discontinuity is. And as we all know that we have various of methods, high resolution methods which recover shock and refraction waves with high resolution, but not many methods are designed to get a very good resolution in contact waves. And we are actually interested in resolving these peaks very accurately. So this was our initial idea, and what the idea is to use the particle method to solve the EPDF equation. And before I explain to you how we use the particle method, I'm giving you a brief idea of what is the particle method is. And in particle method, we look for a solution as a linear combination of delta functions. So here you approximate the initial data by a bunch of particles located at points xi carrying the weight pi. And then what you need to do, you then derive a system of equation for evolution of xi and pi in time. Once you solve the system of ODEs, you get the position of particles and their weight at any time you want, and then the numerical solution is given as a linear combination again of delta functions. Of course, it's just a distributional, it's a weak solution, and in order to get an approximation or to get point values of the solution, you need to somehow recover point values from the particle solution, and we can talk about it a little bit later. So just to give you a brief history, the particle methods have been used first for purely convective problems. They were introduced for the linear transport equation, and I give references here. They will used for solving convection diffusion equations and degenerate parabolic equation. We also applied the particle method with Doron-Levy to solving dispersive and KdV equation, and actually we show that the particle method are capable of capturing soliton behavior of KdV equation very accurately. We used it for modeling of propagation of pollutant in shallow water, for system of pressureless gas dynamics, and the last work on particle method was this work on the PDF equation, which we still continue, and I will talk about what we're doing later. So let me show you how particle method will work for the EPDF equation, and for simplicity of the presentation I will describe it in 1D. So as I mentioned, I'm looking for a solution M as a linear combination of delta function. So what I do, I consider a weak formulation of the problem. Namely, I take a test function, I multiply both sides of the equation by this test function phi, and I integrate with respect to time and space. And after integrating by parts, all the derivative move to the test function, and what I'm doing next, I'm taking this function m super n and substituting this integral. So once I substitute the linear combination of, once I substitute the delta function in the integral goes away, and what I'm left with is just a summation. Okay, so again, I'm taking this formulation, weak formulation of the problem, and substitute the form of the solution in here. And once I did this, I have this system of equation, this equation written in integral form. And now, when I look at the expression here written in red, what I would like to do, I add and subtract to this equation, to this parenthesis in red, dxi dt times phi sub x. What it gives me after I subtract and add it, so I get in this parenthesis now the directional derivative in direction of xi. So I will just replace what is written here by d phi dt, the full derivative of phi in the direction of xi. And then what I will obtain is here is the following formula, where here I have d phi I dt, and the next step will be, I didn't change anything else, so the next step will be to integrate things by part again, and what we obtain finally is this formula written in the bottom of this slide. And when you look at it and you would like this equation to be true for all test functions, you see that this parenthesis should be 0. So the particles dxi dt, their velocity should be given by u. And then you get this two equation, which gives you an ODE for time evolution of the weights. So finally, to summarize what I've just said, if you take this equation, look for a solution as a linear combination of delta function, what you end up with is just the ODE system for evolution of particles which moved with the velocity u, and the ODE equation for the change of the weights of this particle. So you actually, it's the kind of you reduce the given PDE to the system of ODE, and the only thing which you need to know what are these velocities u and ux, and you can easily find those actually by direct computation. You can find this velocity from this Helmholtz equation. Once m is a delta function here, you can invert, like you can do Fourier transform, or you can just solve with, by Fourier transform, and you can easily find the formula for u and u sub x. So the particle method for the EPDF equation is extremely simple. Take this equation, look for a solution in the form of linear combination of delta function, solve the system of ODE where u and ux are given by this formula, and that's it. Obviously, you solve it by a numerical method. You choose your favorite ODE solver, you run these ODEs in time, and you get the solution, and the solution u, the velocity profile, is here. You can recover it at any point x, you just substitute x here, and you get the solution profile. And actually, the truth is that I didn't. This method actually gives you an exact solution as long as the initial condition is, for example, delta function. I didn't do any approximations yet. The only approximation which will be introduced is just a solution of ODE. So far, there is no approximation at all. And here I can show you a couple of examples. It's very simple. If you take one picon, so you take all, like you can take a bunch of particles, all of them will have 0 weight, and only one particle will have weight 1. And actually, it means that you only run one particle. So in order to do this computation, you actually solve a single ODE. Compared to, for example, if you need to solve it by finite difference method, you need to cover the domain with a number of grids. And here we have, for example, 3 picons. They move, they reconnect, and they appear again. And again, it's extremely simple computation because it involves only 3 ODEs. And here I can show you that the linear momentum, the total momentum, the energy of the system is actually conserved exactly with particle method. And I also have here the example to show you how these particles move and they reconnect. And you see the larger picon, he just catch up with a smaller picon, and they reappear again in exactly the same chain as before. And this is a computation which is done with 3 particles. And here, this example which I mentioned before, here you start initially with 2 picons, one positive, one negative. And actually with particle method, you can recover both solutions. So both solutions are physically relevant. Once these 2 picons meet and collide, the one of the solution is 0. And the other solution is just, they collide and they reappear again. And it's just a matter of how you solve the system of ODE numerically. And the truth here is that if you allow, choose, how you choose the delta t actually for the numerical solver. And if you allow particle to jump one over another, so you will recover this conservative solution. If you don't allow particle to jump one over another, so you will recover this dissipative solution. So this is very simple method, and have very nice properties that it turns out that this weak solution of which is obtained with particle method and these systems of ODE can be also obtained from the variational formulation of the problem. And it turns out that the position of particles and their weights satisfy exactly the same Hamiltonian and the same Hamiltonian equation. So the system is conservative, total momentum is conserved, and particle method satisfies the same the necessary properties of the equation. And as I mentioned, one can show that this weak solution obtained with the particle method is actually satisfies the Hamiltonian variational principle in the phase space, and it's a theorem which we proved, and it can be easily shown. The 2D case, so again, nobody actually did it even in 1D with particle method, but in 2D, the situation is even more complicated because less is known about the equation. First of all, it's not known if the equation is integrable, etc. So we here consider, but we started with the particle method, and the idea is to use the particle method to understand the behavior of the solution in 2D. And the idea is the same idea. It's actually nothing new I can add to the picture, just only saying that, again, I'm taking the linear combination of delta function. Now m is a vector, and I can recover the velocity of the velocity u by taking a convolution with the Green's function. just the difference is that for the two-dimensional case, the green function is not an exponent anymore, but the modified Bessel function k0. And but the equations remain the same equation. You still, so this is the system written in coordinate form, and you write each coordinate, each component as a linear combination of delta function. You substitute, you consider a weak formulation of the problem, and what you get is a very similar system of equations. So the particles have the coordinates x and y. They move with the velocity u. So u, v, and v are components of the velocity vector, and you also write down the evolution equations for the weight, where u and v are given by this formula. The only difference is now here that compared to the previous slide, if you see the exact solution u is given by the convolution with the Bessel function, but the problem is that the Bessel function is not defined for x is equal to 0. It's actually blows up at infinity. To infinity. So in 2D, it's become more complicated. You don't really recover the exact solution, because what you need to do, you actually need to mollify the delta, this Bessel function to k0 epsilon is just a convolution of this Bessel function with some mollifier, and this can be done, for example, easily if you take a mollifier as a, for example, as a Gaussian, then you can construct a smooth kernel K, which doesn't have any singularities, by taking a convolution with this cutoff function mollifier, and it turns out that if you use Fourier transform, that this smooth kernel can be very easily and very fast computed by this formula, which can be computed by the Hankel transform, which is the radially symmetric Fourier transform. So this integral is computed very fast. And again, the properties of this is, it turns out that the particles satisfy the same properties as in 1D. It's a Hamiltonian system. Particles and their weight satisfy the Hamiltonian equation, and you can actually derive them from the variational approach, method approach. Moreover, one can prove that the system of particles conserves the linear momentum, and it also conserves the angular momentum. And from these two lemmas, we conclude that the Hamiltonian is preserved. It's not only preserved, but it's invariant under translation and rotation. And actually, for the two-body problem, for two picons, it means that the system is integrable, which is a very nice first step to considering the integrability of the whole system. We cannot prove it in general, but at least this, what we were able to prove, that for two-body problem, it is true. And this actually allows to perform the to perform the first reduction, what is called, namely, to reduce the dimensionality of the problem. So actually, when you have, for example, two picons, what one can do, you can make a change of variables to the center of mass, in a sense, and then run computation only for one picon, and then make the change of variables back. So here's what I showing you, that again, if you have two picons, you switch, you make a change of variables to the center of mass, and then you run your computations, and then you recover the original two picons again. So this can reduce the complexity of the problem, and they make the numerical examples much more efficient than because in 2D already you cannot do it with one picon or two picon. You really need to consider a lot of particles to recover the solution. So this gives you a real advantage over other methods. So let me show you a couple of examples in 2D. So here we have one picon, so simulated by particle method, so it just moves. Here I consider a periodic boundary condition, so it just moves. It doesn't change its shape. We don't see any diffusion at all. It preserves its amplitude. which you can never, this thing you can never recover with finite difference or finite volume method. It just moves, nothing happens. And it's exactly what should happen. Sorry. Here's 2. What did I do? Why it's not moving? So as you see, they collide, they reconnect, and they reappear in exactly the same shape as before. Here's pican, anti-pican simulation, where they become 0 for the moment, and then they reappear again. And again, the nice feature of the system is it's conservative, it preserves the shape and preserves the amplitude. You don't really have any diffusion here. And here, more picons. For this case, I don't have a proof that they should reappear in exactly the same form, but numerical approximation, numerical simulation suggests that this is what happens. Here, they just move, reappear, disappear, and another set of equations which I will show you. Now I will show you some more real examples. They were taken from the paper of Daryl Holm, who's an Imperial College, I guess, in London, and Martin Stelly. So they tried to simulate a more physically relevant initial conditions. And here you have like an initial wave which propagates. You will see how it propagates. But so what they did, they solved it by the finite difference method. So imagine you need to solve it by a finite difference method, so you need to cover the whole domain with the grid, and they actually use the grid 1024 by 1024. So it's a very heavy computation in finite difference method. So I will first show you what you get when you run this. So it's a propagating wave. And again, they used 1024 by 1024 grid, while we were actually able to use, what we did, we kind of lied a little bit probably. We just put particle over here, and this represents the initial condition you saw, and it's only like 400 particles. And when you run, you just run these particles in time, and my picture is just a 3D of what you have here. This just shows you the location of particles, how they move. So all the simulation, I don't have any particles all over the domain. I only put them where I need them. And with 400 particles, I fully recover the same behavior what you can do with the finite difference 1000 by 1000. Here's another example where you have two waves actually interacting. And once again, to run it with the particle method, you don't need to work hard. What you do, you just put 200 and 200 particles nearby, and they run. And this picture shows you how they connect and reconnect.
Also, if you use finite difference methods, you will probably have regularity problems, right?
Yeah.
Because
here you may also.
It's going to go down locally.
Yeah, but here it depends on the initial data. Also, you may have particles which are very close to each other and very far from each other, and you may need to do some redistribution of particles, obviously. But
that's a classical thing.
It always happens. So here's another example where it breaks into two waves. And once again, we started with something like that and show you how particles move. And one more, this example, I guess nothing to do with real application, but I just like it. It's probably very feminine. I don't know, it's just beautiful. I just ran it because I find it being beautiful picture. And this case was run with, again, if I remember correctly, maybe 500 particles, which we put as a star over here, and if you see how particles move in time. So to make it to make it on time, I would just to give you some ideas of what is coming soon. So Jean Gualiu, who was recently visiting here, and student of mine, Terence Pendleton, we are working on the proving of convergence of particle method for the EPDF equation, and actually 1D case is already done. We were able to prove, and while other people do it in a variety of ways, we think we found a very nice and elegant proof, and we actually use the BV estimates. So what we define, so I don't have time to show you the whole proof, but what you do, you define the weak solution of the EPDF, and then you, first of all, you show that the particle solution is indeed the weak solution of the equation. Then you need to show that a number of particles goes to infinity, the particle solution converges to something. This UM is the limit, and this is a very nice proof, which again, you show first that the U itself and its derivative bounded variation function with a bounded variation, and then you use the compactness result associated with the bounded variation. Like the most important that they are bounded, have bounded variations in space in time, and then you know then you use the known result about compactness result associated with BV function to show that this limit exists. Once you show that the limit exists, you can easily conclude that the limit is also a weak solution of the EPDF equation. So this work is done. It's not published yet, but we proved the convergence of the particle method in 1D. We are working on convergence of particle methods in 2D, and also considering the problem of the integrability on the two-dimensional equation, as well as working on the parallelization of this multidimensional code we have, as well as checking the possibility using the variational integrators. Just a small comment that we did implement both variational ODE solvers in just standard Runge-Kutta, and in 1D and 2D we didn't see any difference, because originally people who do work in the dynamical system, they usually don't like to use Runge-Kutta method because they don't believe that, they say that it doesn't preserve Hamiltonian exactly. This wasn't the case here. We just compared, and we actually report in the paper that in this particular case we didn't see any difference between variational ODE solvers and Runge-Kutta, for example. We are working on the development of these variational integrators with the adaptive time steps and some other things, and I will stop here.
Thank you very much. I think the results you presented are very impressive. I don't think the finite difference methods could come close, but I might.
It really depends on, I would say that it really depends on the initial condition. In some cases, no, but if you really need to, if you have a more complicated initial data, which when you will need to cover the initial condition with a lot of particles, then it starts to be more tricky. So I would love to say that the particle method is the best method to use ever, but I wouldn't say it, because I believe there are some examples there will not work as well as I show, but in most examples it probably.
I mean, for kinetic equations they also create
yeah.
problems, but still they work much better than anything else.
That's true. Yeah, that's true.
Well, then there is particle in cell and adaptations for.
So yeah, it might require more work than just a straightforward implementation, but But the most important thing is that it's very low diffusion. It's almost no diffusion, which works fine with these peaks.
Okay, are there any questions?
I didn't catch when you say that depending on the time steps, you can catch two different solutions, which means that the system has not a unique solution.
No. So the system has infinitely many weak solutions.
But then there is a principle to
And
select.
there is a physical. They believe that the physically relevant solutions are two of them. One, which is it's called dissipative. So if you look, so when we worked on the proof, so you can, on the convergence proof, this convergence proof, you recover the, there exists a unique solution of the ODE system for any time until particles collide. Okay? So I would say that this proof, for example, of convergence to the solution is valid for any time until particles collide. Now, you can prove that for any time t bigger than 0, there is no particles located in the same place. So the solution exists, unique solution of the ODE system exists globally. It's not a very simple proof. However, if you look at this proof and this convergence, you will recover only this dissipative solution. When they collide, it's 0. That's it. They believe that the physically relevant, the one where they reconnect and reappear again. And it's only numerics which recover.
So this is some kind of entropic principle?
Yeah, but there's no entropy, I don't know.
Right, exactly.
So exactly, thank you for saying this. If you think about this equation to be reversible in space and time, if you consider that it's symmetric, u of xt is equal to u of negative x negative t, then you have this conservative solution where they reappear again.
That comes from the Hamiltonian.
Which comes from the Hamiltonian. If you just if you don't take this reversibility into account, then it's only 0. But numerically, funny that it depends on how you run the ODE solver. When particles move and get closer and closer, if you choose adaptive time step and don't allow particle, the time step depends on the distance of the particles, they move closer, 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 but they never jump, so it will be 0 solution. If you run it with a constant time t, and once they hear, they just jump and go further, then...
So if you use the finite difference method, you'll probably never see this problem because you would introduce artificial dissipation.
And it will go 0, yeah, it will go 0. This is why it's important to have not the dissipative method. So there are some papers with discontinuous Galerkin, and Chivang Shu has a couple of papers, and people in Norway, they work, but they were never able to recover this anti-picon interaction.
Last question.
Would it be possible if you have two negative peaks colliding to 0?
No, they move in the, if they move in the same direction, but the speed is proportional to the amplitude. So the larger will be.
My question is, if the ones make the 0, right, and it's not dissipative, are there also solutions where out of 2 or something?
Yeah, I showed when you have two positives, small and large overtakes the small one, and then they reappear again. It's like solitons, but it doesn't. Here, it doesn't matter if it's positive or negative.
Don't cancel completely, right?
Yeah, no, but they cannot because they're always positive. Here, you can have positive and negative, and this is why you get 0.
Yeah. Oh, yeah. Also.
Okay, so it's in the solitons you cannot have negative one.
Okay, if there are no further questions, and we will have a 15-minute break. No, is it? Is that a schedule?
15 minutes at 3.
15-minute break. Thank you, Alina.